today's class, we're going to be looking at electricity. So, and then we're going to be looking at light. So, electricity and then light. So, under electricity, we are just going to branch it into, I think we've discussed static electricity in our previous video. So, in this particular one, we'll just work on current electricity. Okay, we just have to finish the static electricity. Static. So under which we talk about Coulomb's law of electrostatic, coulombs. Then this we talk about the current electricity, and that is going to be on DC. We're just going to restrict ourselves to DC. So then under light we'll talk about reflection, and we'll talk about refraction. So these are the ones we're going to talk about in this video. So let's start with electricity. And okay, so now when we talk about the static electricity, which is the study of charged body at rest or in slow motion, so we have terms we need to discuss. You get, so we're going to look at, we have discussed the distribution of charges around the conductor, so which helps to explain that when a conductor has a sharp edge, charges are more concentrated at the sharp edge of the conductor, while on the other part is going to be distributed evenly except the sharp edge. So if you have this, which means charges will be distributed evenly, and if you have something like this, so charges will be more concentrated here. So, and that is the principle used in building the thunder arrestor or the lightning conductor, so which will definitely conduct more of those charges and then take them through the earth cross by the part of conductors connected directly to it. So that is for this. So then we'll look at point charge and what might be happening between them. So that will take us to Coulomb's law. Coulomb's law. So under Coulomb's law, if we have a charged body Q1 and we have a charged body Q2, and they are at certain distance apart, so let's say the distance is r, so there exists a force of attraction between them. So if they are opposite charges, if they are the same charges, there exists a force of repulsion between them. So this force is accounted for by the Coulomb's law of electrostatic. So this law states that the force of attraction between these two charges is directly proportional to the product of the two charges and inversely proportional to the square of the distance between them. So we can interpret that mathematically as the force of attraction directly proportional to the product of Q1 dot Q2, and the same force is inversely proportional to the square of the distance between them. So when we have this, what do we need to do? We just have to merge these two expressions together in a joint variation. So then we have a F directly proportional to Q1 dot Q2 over r squared. So having this, I think we need to introduce a constant, which is Q1 dot Q2 all over r squared. So the value of K is definitely equals to 1 over 4 pi epsilon naught. So, and then what does epsilon stand for? Is permittivity of free space, is the permittivity of free space. So the value of K as a constant is K equals 9 times 10 raised to power 9, and the unit will be when you make K the subject of formula here, so you're gonna get Newton per Newton meter squared per Coulomb squared. So that is actually the unit of K. So we can lay our hands on questions on this. So that is for this, that's for Coulomb's law. Then we have another part we need to talk about. So based on static electricity, we have electric field intensity. So electric field intensity E is more or less like the force that acts per unit charge in an electric field. So if I have a charge Q, take for instance a charge Q in an electric field, so the electric field intensity that tells us how strong the electric field is equals to the force which acts per unit charge Q. So we can derive an expression for this also using F. Since F is equals to KQ when Q2 over R squared. So when we have this, we are dividing this by times 1 over Q. So which means it has to involve just a single charge. So we can just take this off and we have electric field intensity equals KQ over R squared. So which now is concentrated on just a single charge body. Okay, so now that is for that. So we'll move to the next aspect. So these are the formulas you could use in solving various questions. So now talking about direct current now. Direct current, I think we spoke a little bit about it in our previous direct current. So that is DC. So we said current is denoted by I, and this means electric current. Electric current, and it represents the continuous flow of charge body in a conductor. So meanwhile there must be a friction along their paths to move, so which is resistance, and we must have work done in taking the charge body from one point to another to be potential difference. Potential difference. However, we still have the force that brings out the current from the battery, so that is EMF. So we know that as EMF, of which the full meaning means electromotive force, which is the driving force for the current to be out of the battery. So that is electromotive force. So now I established a relationship between V, I, and R in the previous video, and that is Ohm's law, which I've stated in the previous video. So but let's establish the difference, the relationship between this. So we can also write a formula connecting this 4. So and that is going to be E equals I R plus I R. So now you could be asking, what is the difference between the big R and the small r? So I'm going to draw a circuit to explain that. So now don't forget, before I draw the circuit, I told you that current flows in a conductor, and what makes this possible is because there is a frictional force along their path, so and that is the resistance. So this R represents the external resistance of the conductor once the current leaves the battery, while this R represents the internal resistance of the battery, that is the resistance within the battery when the current is driving out from one terminal of the battery to the other end and then out to the exterior, which is the conductor. So this now is the resistance that would be for the external, so why this is the internal resistance. So the value of these could be measured on voltmeter, because if you look at Ohm's law, which means this is V equals IR, so Ohm's law is this. So the value of V with this IR could be noticed on the voltmeter connected in the circuit. So let's draw a circuit now. So let's assume we have the cell, which is the battery. The longest part is the positive. So this longest part is the positive, and then the smallest part is the negative. So if we connect these two, the resistor, this is the resistor, and then the voltmeter will be here to measure potential difference. Then you have ammeter here to measure current. So and then they are connected in this manner. So the voltmeter have to be parallel with the resistor. So and this is the cell with EMF E. So now when current flows out from the battery in this direction, it flows from the positive terminal. This record the quantity of current in the circuit. So by the time it got here, so this will measure the potential difference, which is only IR. So this particular one could not be measured here, so we call it lost voltage, lost, so which is IR. So it means this formula is just the lost voltage plus the one that could be recorded on the voltmeter. So this is the relationship between them. If you factorize I, you could get a relation like I equals E over I plus R. So that is another relation you could get from that. So now, apart from this, now we need to talk about the arrangement of resistors. So how do resistors arrange? Take for instance, I'm in a lab and I need a 1 ohm resistor, but I couldn't find this, so I just have to arrange multiples of 1 ohm resistor in such a way that, okay, I couldn't find 1 ohm resistor, but I only have 2 ohm resistor, so I would have to use a way to arrange the 2 ohm resistor to give me the 1 ohm resistor. So probably if I need 2 ohm resistor and I have 1 ohm resistors in the lab, so all I need to do is just to arrange the 1 ohm resistor in certain arrangement to give me 2 ohms. So now let's talk about how is the arrangements look like. So now, so still on direct current, we're looking at arrangement of resistors, of resistors resistors. Now don't forget I told you that resistor is a device that offers resistance. So meanwhile, resistance is the amount of opposition given. So now, if we had to draw this in a circuit diagram, so take for instance, we have, okay, let's take the two types of arrangement. We have the series and we have the parallel. You see, for the series arrangement, they are arranged in such a way that the same current flows through them. So let's check the series arrangement here. So for the series, so if I have the source of current here, okay, let's say the current flows in this direction. So resistors will be in series if the same current flows through them. So let's assume voltmeter is attached here. So look at this now. When current comes here, so this is a node, a junction. So because currents have to move like this, okay. So when current enters here, so the same current that splitted here, the current wouldn't be splitted into two equal parts. So this is current I, and the current that we enter here is going to be what? I1. So the same current we get here, I1, I1. So different current, which is I2, will flow in this direction. So these are in series because they got the same current in them. So for the fact they have the same current, their potential difference will be different. So which means this we have a potential difference V equals I1 with the value R1. So this we have the potential difference. That means the total potential difference recorded by the voltmeter is going to be equals to this plus I1 R2 plus I1 R3. This shows they have the same current in them, so we can factorize. Don't forget it, sum of all the currents must be equals to I. So don't forget it. Don't worry about this I too, okay. So we can just make this I, then the total resistance in the circle R, in the circuit R, is gonna be, okay, let's factorize this. So we have I into R1 plus R2 plus R3. So if this cancel this, so which means the total resistance in the circuit will just be the addition of all the resistance that are arranged in series. So we have total R equals R1 plus R2 plus R3 plus Rn. So that is if more than 3 is connected in series. So which means when you have resistance in series and you want to know the total resistors that you have connected, the total resistance offer, just add the values of the three or more resistance connected in series. So it's quite simple, so just do that. So now we move to when they are connected in parallel. Okay, let's take for instance we have the source of current here. So and then you have a resistor here. Okay, let's put it this way. And we have a resistor here. Okay, this is the source of current. So you believe me that these resistance have different currents in them. So this is I1, I2. So and this is high. So the different current flows through them. So when they have different currents, they will have the same potential difference. So which means the current I, which is the total current, must be what? I1 plus I2. So now don't forget that from Ohm's law, we knew that V equals IR. Okay, so which means I would be what? V over R. So if and this R is going to be total, so the total resistance offered in the circuit is what we're trying to get. So we can put this as V over R total. So then this would be V1. Okay, they have different potential difference, so we have to take it as V1 over, okay, sorry, they have the same potential difference, so we can have to take it as V1 over R1 plus V2 over V over R2, sorry. So don't forget in series that they have different potential difference, but here in parallel they have the same potential difference. So which means this is V over 1 over R total equals V into bracket 1 over R1 plus 1 over R2. So then, which means the total resistance in that circuit is going to be 1 over R total equals 1 over R1 plus 1 over R2 plus 1 over Rn. So that indicates that you connect more than one. So E to be equals to the sum of the reciprocals of the resistors connected. So now let's move on to electrical energy and power. So what do we understand by electrical energy? So when a charged body Q is moved from a point A to another point B, there is a work done, just like when you say force is applied on a body to travel a distance, so there is always a work done. So the work done, which is W, will be equals to there is a potential difference developed whenever a charged body move from a point to another. So that is the potential difference at this point is VA, and the potential difference here is VB. So which means the charge multiplied by the change in potential difference would be the work done in the circuit. Yeah, so if we subtract this to give us V, we can say W equals QV. So don't forget V would be what? VB minus VA. Okay, so now this is one thing we need to know, and then let's bring back what we have into it from Ohm's law. So now this is the electrical energy or work done. So we can also bring this out to work on. So I want to use this now. W equals QV is what I want to use. So how do I use it? So I can just take it from Ohm's law that don't forget Q equals IT. This is not really Ohm's law, so this is current times time. I don't know if I've given you that. So whenever current passes through a conductor or a circuit for a given time t, there is always charge developed. So we can make this work done equals high Vt. So this is one formula for the electrical energy. Then we can also substitute others since V equals IR. So we can put that as, if since V equals IR, we can put this as a high when IR multiplied by T, so that will give us high squared RT. So take note, you're going to take some questions on this during the class. So, and then you can substitute as much as possible into it and you get your answer just based on Ohm's law. So you can also make high the subject of formula, then substitute high here, so you get what you want to get. So that is it on electrical energy. So then the electrical power, we define power as the rate of work done, and you can define work done or electrical energy as the product of the charge developed in a body or in a circuit multiplied by the potential difference using this relation. So then if you're talking about electrical power, so power is always the rate of work done, so which means power is work done over time, and power is measured in watts denoted by P, and it's measured in watts. Okay, watts is actually the unit. So now plug in the formulas of work done into it, so which means power could be what, I v t over t, so which is IV. Power would also be I squared RT over T, which is I squared R, and so on. So this is electrical energy and power. So we would solve more questions. We'll talk about buying of power in the next video. Okay, so let's quickly touch the parts of lights. So then if we don't finish electrical work done today and we don't finish light today, we're gonna complete the duo in the next slide of video and the next class. So let's quickly look at lights so that we can fulfill what we said we're gonna do in the video. So now when we talk about light, what does light means? So light is what we want to talk about, and light is just like the sensation in vision. So when you say light, the sensation in vision, so we just want to talk about the reflection and then refraction. So now when light travels and they actually hit an obstacle, the light tends to repropagate. Take for instance, how do you see yourself in a mirror? It means the ray of light that falls on you falls on the mirror, and then the reflection of the ray of light goes back to your eye and you're able to see yourself. So let's go to reflection and talk about reflection. So reflection is just like the bouncing back of light when it hits a reflective material. So not all material could reflect light. So materials that could not reflect light, they have a rough surface and they create a kind of diffuse reflection. And we have opaque material, so light is unable to pass through those kind of materials. So instead, so I call it opaque material. So then we have materials that are transparent. Transparent materials, we allow light to pass through them, just like glass, water, and so on. Those are transparent medium. So but we are going to look at transparent medium in refraction. So then we're talking about reflective surfaces in reflection. So let's talk about reflection. So reflection is the repropagation of light when it encounters a reflecting surface or a reflecting obstacle. So let's take for instance, you have this line as a reflecting surface. For every reflecting surface, there must be a line that represents the normal n. So n is called normal, which must be drawn on any reflective surface. So now the ray of light travels at an angle to the normal, so we call that the angle of incidence. So the direction of ray of light must be shown so that you could know where it is coming from. So now on this reflective surface, the light reflects or bounces at the same angle, which we now call angle of reflection. So this property of light is called reflection, the change in direction, the repropagation of light when it encounters a reflective obstacle. So that is an obstacle that have the ability to bounce back the light. Okay, so now let's proceed on that note. So this is angle of incidence, this is angle of reflection. So if I name this O, so and this is A, and I name this B, so it means O A represents the incidence ray or incidence ray, then OB represents the reflected ray. So high represents angle of incidence, while R represents angle of reflection. So these are the property you need to know. Then we have the laws of reflection. The laws of reflection. So the laws of reflection. What are the laws of reflection? We have just two laws. So the first law says that the incident ray, that is the incident ray O A, the normal ray, that is N, or you call that O N, and the reflected ray, so OB, all lies on the same plane. All lies on the same plane. So this is giving us the impression that OA, OB, and ON are all on the same plane. So that is the first law of reflection. Then we have the second law, and that just tells us that I is equals to R. So which means the angle of incidence is equals to the angle of reflection. So which means this angle here will be called angle of glance. So G is called the angle of glance. Angle of glance. Angle of glance. So then if I is 30 degree, definitely, since according to second law, I equals R, so here we also be 30 degree. So the sum of the two gives 60. So and these are also equals to each other. So the sum of angle on a straight line is 180. So 60 minus 180, we have 20. So which means each G will be 60 degree each. 60 degree. However, if I extend the angle of incident to the behind the mirror in a virtual form, I have an angle here which is angle of deviation. So angle of deviation D must be equals to 2G. So these are what we need to know based on the properties of the mirror, reflecting surfaces. So then we have the application of reflection. So talking about the application of reflection, we'll look at applications. So under the application of reflection, we'll be considering what we call periscope, kaleidoscope. So periscope is just a device used to view over obstacles. So it consists of two plane mirrors. So this is placed at angle 45 degree. So then we have this. So another mirror placed here. So these have to be tall so that when these observe something over obstacle, the ray coming from this side falls on this mirror and then reflects on this other mirror, and then the reflection is transferred to the viewer at this point. So the viewer would be able to see what is going on at this side, even if we could not. So if there is an obstacle in vision. So then kaleidoscope is just like a toy used as like a camera toy for kids. So it operates by the principle of reflection. So now let's quickly look at refraction. So what does refraction means? Refraction occurs in transparent medium. Refraction occurs in transparent medium. So and what what is refraction? Refraction occur when ray of light travels from one medium to another, and then because of the density of the medium are different from each other, so the light ray have to bend towards the normal in the other medium. Take for instance, if this is glass, so I told you there is always a normal. Now a ray of light is traveling from air into glass. So if this is air, this is glass. So and then the density of glass is higher than that of air, so which is less, this air is less dense and the glass is denser. So we have the angle of incidence here, and this is incident ray. So then the ray of light will not proceed in a straight path, so it's going to bend to this angle r, which is angle of refraction. Okay, so and then the ray here is refracted ray in the other medium. So refraction can be defined as the change in direction of light when it exceed one medium into another medium of higher density. So now, and it also take place from medium of higher density to medium of lower density. In such case, we have some properties like total or internal reflection, and then we have certain angle that lead that if the ray of light from the denser medium exceed that angle, we have total internal reflection, and so the angle is called critical angle. So now we have laws of refraction. The laws of refraction is telling us that the angle of, okay, let's say this is A and this is B and this is O. So OA, OB, and N all lies on same plane. That's the first law of refraction. So the second law is telling us that the sine ratio, that's the sine of the angle of incidence to the sine of angle of refraction is equals to a constant. So the constant is this. So and this constant is called refractive index. So we call this a refractive index. Refractive index. So this refractive index is the refractive index of a medium of air to glass. So if the ray is traveling from glass to air, so the refractive index from glass to air will now be inverse of the refractive index